Hello everyone, welcome to the channel Top Gate. In this video, I will discuss few more examples of the shortest remaining time first algorithm. So without wasting any time, let's just go straight away to the example. And in this example, we have been given 4 processes, and for those processes, we have been given the arrival times and the burst times. With the help of this scenario, we have to draw the Gantt chart, and with the help of the Gantt chart, we have to calculate this turnaround time and the waiting time. Fine. So I haven't written the exact statement of the question here, but in most of the questions, they usually ask you what is the wait time, what is the average wait time, what is the average turnaround time, and so on. Clear? So let's quickly go to the Gantt chart. So I'll draw the Gantt chart here. So initially we are at time 0, and first of all I'll see that at time 0 what are the processes which are coming into the RAM. So this is the time at which the processes are getting into the RAM. So if we see this one, we can see that P1 is coming at time 0 into the RAM. So we are at time 0 right now. So at time 0 there is only one process in the RAM. So we don't have any option right now. We don't have any competition. We just have to schedule P1 right now. And what we are doing? We are doing the shortest remaining time first algorithm. That is, the priority is given to that process who is having the shortest burst time. So if we see this one, if we analyze this burst time, so we can say that process P2 is having the highest priority. Why? Because its burst time is the shortest. But currently we are at time 0, and this process P2 will arrive at time 1. So I don't have any option. I have only P1 in the RAM right now. So I will schedule P1 at time 0. So I'll start with P1, and this P1, it will try for 8 units. So it will try to execute for 8 units. So it will start at 0, and then as soon as it reaches 1, you can see that P2 arrives at 1. Fine. Now I'll see that till time unit 1, how many units P1 has executed. So we can see that P1 has executed exactly 1 unit till now, that is 7 are still left. And at time 1, P2 process came whose burst time is 4. Now we will compare the remaining time of P1, that is 7, with 4. Now 7 and 4, which one is shorter? So I can see that P2 is shorter. Therefore, P2 will be able to preempt P1 right now. So P1 will be stopped right now, and it will be sent to the waiting state, the block state, and P2 will take over the system right now. Clear? Now P2, since it is the shortest burst time in this one, therefore no process will be able to preempt this P2. So P2, if it starts, it will continue for its complete 4 units. So it will start at 1 and it will continue till 5, and it will complete its 4 units, and it will now terminate and go out of the RAM. So this P2 does not exist in the RAM at all right now. Clear? Now currently we are at time 5. So I'll see till time 5 what are the processes which are arrived into the RAM. Clear? So I can see that till time 5 I have P3 also in the RAM, I have P4 also, and P1 which came at time 0. So currently at time 5 we have P1, P3 and P4. Clear? So out of P1, P3 and P4, we have to see which burst time is the shortest. Clear? So this P1 is 7, P3 is 9, P4 is 5. So 7, 9 and 5, the P4 is the shortest one. Therefore, P4 will take over the system, and since it is the shortest one out of the available processes, therefore no one will be able to preempt it. Hence, it will start at 5 and it will complete its work at 10, and its work is done. It will also be terminated. Now in the RAM we have only 2 processes. We have P1 with 7 burst time, we have P3 with 9 burst time. So obviously P1 is having burst time of 7, which is shorter. Therefore we have to schedule P1 now. So at 10, P1 will take over the CPU and it will complete its remaining 7 units. So it will go till 17, and then it will also terminate and go out of the RAM. Now there is only one process, that is P3 in the RAM. So we will schedule P3 here, and this P3, since it requires 9 units, so it will start at 17 and it will go till 23. 6. So it will also complete and terminate and goes out of the RAM. So this is the complete Gantt chart right now, and with the help of this Gantt chart we now will calculate the completion time, and then completion time I'll go to the turnaround time and then the waiting time. Clear? So let's quickly calculate, see the completion time in this one. So for P1, what is the completion time? P1 is coming in 2 iterations, the first iteration and the second iteration. So P1 is finally completing its work at 17. So I'll simply write 17 here. For P2, P2 is coming in only single iteration. It is completing at time 5. So I'll write simply 5 here. And P3, it is completing its work at 26. So I'll simply write 26 here. And P4, it's completing its work at 10. So I'll simply write 10 here. So now we have to calculate turnaround time. So turnaround time is completion time minus arrival time. So simply I will first write all the completion times. Clear? And then I'll put minus signs. And now the arrival times. Arrival times are 0, 1, 2, 3. So I'll put 0, 1, 2, 3. So 17 minus 0 is 17. 5 minus 1 is 4. 26 minus 2 is 24. And 10 minus 3 is 7. Clear? And now the waiting time. Waiting time is turnaround time minus burst time. So I'll simply write turnaround time right now. That is 17 and then 4. And then 24 and then 7, and then I'll simply put minus sign here and then the burst time. So now the burst times are 8, 4, 9, 5. So 8, 4, 9, 5. This marker is not working, right? So let's calculate this one. 17 minus 8 will give you 9. 4 minus 4 will give you 0. 24 minus 9, that will give you 15. And 7 minus 5 will give you 2. So we have got the turnaround time of the individual processes, and we have got the waiting time of the individual processes. So now let's calculate the average waiting time and the average turnaround time. So the average waiting time will be, it is 9, 0, 15, 2. So 9 plus 0 plus 15 plus 2 and divided by, we have 4 process. So I'll put 4 here. Clear? So 9 plus 0 is 9 plus 15, that will give you 24, plus 20 plus 2, that is 26 by 4, that will give you 6.5. And now the average turnaround time, that is 17, 4, 24, 7. So 17 plus 4 plus 24 plus 7 divided by 4, and that will give you 17 plus 4 is 21. 21 plus 24 is 45. 45 plus 7 is 52 divided by 4, that will give you 13. So this 13 is your average turnaround time and 6.5 is your average waiting time. So now let's quickly do the next question. So this is another example of the shortest remaining time first scheduling algorithm. In this one also we have 4 processes, and we have been given the arrival times and we have been given the burst times. Now you can notice in this one that the burst times, we are having 2 burst times as the same, that is 3 and 3, that is there is a tie. And remember my very first video about the shortest remaining time first scheduling algorithm, in that one I said that if there is a tie, the tiebreaker is always a FCFS. Fine. So if 3 and 3 they are together, I mean their priority is same, their burst times are same, and they are coming at this one is coming at 1, this one is coming at 2. So in that case we will see which process is arriving first. So in case of tie, we just have to use the FCFS algorithm. Clear? So let's quickly solve this question, and we have to find out the Gantt chart, and with the help of the Gantt chart we will find out the turnaround time and the waiting time. Fine. So let's quickly make the Gantt chart. So in the Gantt chart, we are currently at time 0, and I'll see that at time 0, what are the processes which are coming into the RAM. So at 0, only P1 is coming, so I don't have any option. However, its burst time is 5, its priority is the least, but since at time 0 it is the only process, so it is having the highest priority at time 0 as for now. Okay, so at 0 this P1 will start and P1 will try for 5 units. It will try whether it is getting executed or not, but it will try for 5 units. So it will start at 0, and as soon as it reaches 1, you can see that P2 has arrived. Now P2 has arrived at 1. Now at this point I'll see that till time 1 how many units P1 has executed. So till 1 P1 has executed only 1 unit, that is out of 5 it has executed 1 unit. So how many left? 4 are left. Okay, so we are currently at time 1. P1 is left with 4 units and the new process P2 is having 3 units. So out of 4 and 3, 3 is the shorter one. Therefore, P2 has the highest priority. Therefore, P2 will be able to preempt P1. So P1 has to stop here at 1. It will go to the block state, the waiting state, and wait there for its turn. And meanwhile, P2 will take over the CPU. So P2 will come at time 1 and it will start executing. So it will start at 1 and it will try for 3 units. Clear? So it will try. So it will start at 1, and as soon as it reaches 2, you can see that P3 arrives. Fine. Now at time 2, this P2 has executed 1 unit and this P3 is having 3. So the remaining time of P2 is 2. That is, we have done 1 unit for P2, so remaining is 2. So the remaining time of P2 is 2 and the burst time of P3 is 3. So out of 2, 3, P2 is the shorter one. Therefore, P2 will continue. P3 will not take over the system right now. Why? Because it is having the burst time more than the remaining time of the P2. Clear? So P2 will continue and it will go till 3. At 3 there is no process. It will go till 4 and at 4 it will complete its work. Fine. So 3 is done. That is, P2 is completed and it will terminate and go out of the RAM. So now this P2 does not exist in the system at all. So currently we are at time 4, and at time 4 I can see that P4 has also arrived. So right now in the RAM we have P1, P3 and P4, and out of these 3 I'll see which one is the shorter one. So P4 is the shortest one, which is having only 1 unit of burst time. So obviously P4 will take over the system and P4 will start at 4, complete its work at 5. It will also complete and terminate and goes out of the system. Clear? So now at time 5 we have P1 and P3 into the RAM. So out of P1 and P3, P3 is the shorter one, so it will take over at 5 and complete its work at 8. So it will also get terminated, goes out of the system. Now the only process P1 is left, which is having 4 units of time. So it will start at 8 and complete its work at 12. So it will also get terminated and goes out of the system. So this is the correct Gantt chart for the shortest remaining time first scheduling algorithm for this particular example. Clear? So now let's quickly calculate the turnaround time and the waiting time. So what is the completion time for P1? So for P1 it is coming in 2 iterations, this one and this one. So the second iteration is completing at 12. So I'll write 12 here. For P2 it is completing at 4. For P3 it is completing at 8. For P4 it is completing at 5. So now turnaround time, we know it is completion time minus arrival time. So I'll quickly write completion time 12, 4, 8, 5, put the minus signs, and then the arrival time 0, 1, 2, 4. So 0, 1, 2, 4. So I'll get this as 12, this is as 3, this is 6, and this is 1. And then the wait time, we know the wait time is the turnaround time minus the burst time. So turnaround time we have already calculated. So it is 12, 3, 6, 1. Put the minus signs and the burst times. Burst times are 5, 3, 3, 1. So I'll simply put 5, 3, 3, 1, and then 12 minus 5 is equal to 7, 3 minus 3 is equal to 0, 6 minus 3 is equal to 3, 1 minus 1 is equal to 0. So now let's quickly calculate the average wait time. Average wait time, we know it's 12, 3, 6, 1. Sorry, it's 7, 0, 3, 0. So 7 plus 0 plus 3 plus 0 divided by 4 processes. So it will give you 7 plus 3, that is 10, divided by 4, that will give you 2.5. And then the average turnaround time, it is 12,361. So 12 plus 3 plus 6 plus 1 divided by 4 process, that will give you 12 plus 3 is 15, 15 plus 6 is 21, 21 plus 1 is 22, so that will give you 22 divided by 4, that will give you 5.5. So the average turnaround time is 5.5, average waiting time is 2.5. Clear? So this shortest remaining time first algorithm always produces the least waiting time. Clear? Thank you so much.